Okay, today I'm going to show you how to derive the arithmetic series formula from the arithmetic sequence itself. And an arithmetic series is simply a sum of all the elements of an arithmetic sequence itself. So here's a couple of assumptions we need to get started in order to understand how we come up with this proof. First, in the arithmetic sequence, we assume that we have n terms. There's a list of n terms. And the reason why we have n minus 1 here times d, which is the common difference, instead of nd, is so that if we were to go and plug in a starting number that we first start counting at, in our words, n equals 1, we would actually end up getting u sub 1 term back. So we have u sub 1 here, u sub 1, I plug in 1, it becomes 1 minus 1 times d. That simply disappears because it becomes 0, and you get u sub 1 equals 1, u sub 1. If I were not to do that and I were to say define it as, so let me put a what if, as u sub n equals u sub 1 plus nd, then if I were to go and put in, define u sub 1, I would get u sub 1 equals u sub 1 plus d. And that would be a contradiction because if I subtract that on both sides of the term, I get that the common difference equals 0. Which that means we don't even have an arithmetic sequence in the first place, so that will not do. So that's why we need this convention. But having said that, we define that like d is the common difference. And u sub 1 is the initial term. Now, in order to derive the arithmetic series formula, we're going to actually solve a much more simpler problem, which is to go and find the sum of arithmetic series of common difference 1. Or in other words, the sum of consecutive integers being added together. So we're going to find s as an arbitrary sum with a starting term being 1 and a final ending term being n. We're going to sneakily create another copy of this just because we can. And we're going to replace the order of n and 1 because for finite sums, addition is commutative. Note, I say this for finite sums. This doesn't work if your sum is infinite. And then just simply using the laws of algebra, we'll add these two together. And we get a string of n plus 1 addends. Now, how many n plus 1 addends do we have? Well, we said that our arithmetic sequence has n terms, right? So naturally, there would be n of them. And then you just multiply it by the counting principle. Now, simply divide by 2. And you get n times n plus 1 divided by 2. This is also known as the triangular numbers formula, which gives us the number of dots if you were to construct an equilateral triangle using them. So using this example, and we let n equal the row number, largest row number, this will give us the total number of dots that we have in this equilateral triangle construction. But anyhow, that's a quick digression to something that's great prominence in figurative numbers. Now let us go and see how we actually get the arithmetic series in general. So notice all we did here is that we had 1 and n here be our initial term, and n be our final term in the sequence. If we were to go and generalize this for any kind of common difference multiple being added, we just replace 1 with u sub 1 and n with u sub n. And then we simply replace u sub n with the arithmetic sequence formula you saw at the very beginning, n minus 1 times d. And that's it. That's the arithmetic sequence formula, all done and handy.